Hello. So I want to talk about Cantor set and something called Cantor function. Um, so the reason that I got in touch with the Cantor set is at the end of 1.5, section 1.5 in Poland, which is the section that talks about the Braille measure. He gives us some examples about the set that is extremely large, but it has a measure really small. So Cantor set is one such example. We'll see later that the measure of Cantor set is actually equal to 0, but the Cantor set is actually compact and well, it just extremely large. I feel like we will prove one of the propositions that that mentions some of its properties. Okay, but at the beginning, let me just define Cantor set. Okay, so the most common expression, or the one that you encounter in your undergraduate real analysis, is so the first so it's kind of like we are in 0, 1, right? And then we remove this one. We only focus on this, and then so we have this, and then we remove the middle, and then we only have 4 of this, and then for each of them I split into 3, and therefore so forth and forth. So we get some. But today I want to mention one general expression. It is called base 3 decimal expansion for the digital point in 0, 1. So let's talk about the Braille. So we're talking about the Cantor set on the interval 0, 1. I think that's how the Cantor set defined. So anyway, we're on 0. We're on the interval close interval 0 and 1. Okay, so first of all, before we introduce Cantor set, we're going to introduce an expression, and that expression has a name. It's called base 3 decimal expansion. I'm gonna highlight this. Okay, so for every x in 0, 1, x can be written into 1 to infinity of aj to the power of negative j, where aj is equal to 0, 1, or 2. So it's kind of like you have an infinite series. It's like infinite linear combinations of 3 to the power of negative j. And the coefficients in front can have any linear combinations. For example, so for example, okay, I have a interval 0, 1. Okay, and this is 1 over 3, this is 2 over 3. If my x is over here, that means this implies a1 is equal to 1. Okay, and if I have x over here, that implies a1 is not equal to 1. And then if I have furthermore an x over here, for example, so that implies a1 is not equal to 1 and a2 is not equal to 1. If I have a set 1, 2 is here, that means a1 is not equal to 1, a2 is equal to 1. So that's how we define how we express every point in the closed interval 0, 1 into base 3 decimal expansion. Okay. This expansion is unique unless X is of the form. So unique unless X is of the form P times 3 to the negative K to the power of negative K, where P and K are integers. So let's just give some examples. Okay, so for example, 1/3 is equal to 1 times 3 to the power of negative 1. 2/3 is equal to 2 times 3 to the power of negative 1. 2/9 is equal to 2 to the power of 3 over negative 2. And so on and forth, right? So we have all these examples and they satisfy in this form. So unless, what does that mean unless? So it's not unique. The expression above is not unique cases. So so that means we have two expressions for those points. So the expansion form 1 is aj is equal to 0 while j larger than k, and then the expansion form 2 is aj is equal to 2, I think, for all j that is larger than k. Okay, and so for example, let's show some examples. Okay, so here p is equal to 1, k is equal to 1. Here p is equal to 2, k is equal to 1. Here p is equal to 2, k is equal to 2. Okay, so for this case, 1/3, it should be a1 3 negative 1, and then for a2, right? Because k is equal to 1, and then 2 and the others are larger than 1, so it's just going to be 0. Okay, and then you can see that the a1 should be 1. And then for 2/3, well, with a1 again, the power negative 1 plus, again, k is equal to 1, so the others are 0. And then for 9, 2/9 is equal to a1 times 3, negative 1 plus a2 times 3, negative 2. And all the others are 0, so I'm going to write 0. Okay. And then, so by looking at, you are able to figure out what are a1's coefficients. For example, here 1 and here should be 2, and here it can be 0, and here it could be 2, right? And then the expression 2 from 2 is, so 1/3 is equal to a1 times 3 negative 1 plus, because k is equal to 1, so now we're doing k is equal to 2, right? So it's going to be 2 times 3 to the negative 2 to negative 3 is 3 plus dot dot dot. And then 2/3 is equal to a1 3 negative 1 plus 2 times this plus 2 times this. And for this, so a1 3 negative 1 plus a2 times 3 negative 2 plus, so k is equal to 2 in this case. The others are 0, so we have 2 times 3 negative 3, 2 times 3 negative 4 plus dot dot dot. Okay, so that's the form of expansion. And Can we determine the coefficient in this way? For example, what is A1? What should A1 be? Okay. Well, we have 1/3 is equal to A1 times 3 negative 1 plus 2 times J is equal to 2 infinity 3 negative J, right? That is equal to A1 negative 1 plus 2 times 3 to the power of 2 times 2 equal to J is equal to 0 infinity 3 negative. And this, so A1 3 negative 1 plus 3 negative 2 plus 2 times this 3 negative J. So this is equal to 1. So A1 plus 3 negative 1 plus 3 negative 2 times 2 times 3 over, let's see, 3 over 2. Because this is equal to 1 over 1 minus 1 over 3. So this is 1 over 2 over 3, which is equal to 3 over 2. And you times 2, which is equal to 1. Okay, so this is A1. I'm sorry, so this is multiply times 3 negative 1 plus 3 negative 2. So we have 1 over 3 minus 1 over 9 is equal to A1 times A1 times 1 over 3. So this is 1 over, this is 3 over 9 minus 1 over 9 is equal to A1 times 1 over 3. Then we have 2 over 9 is equal to A1 times 1 over 3. And A1 is equal to 2 over 9 times 3, which is equal to 2 over 3. Sorry, I found that only in my calculation. So where's my mistake? I forgot times. This is not equal to 1. I'm sorry, this is equal to 3. So what do I have is I have A1 over 3 plus 1 over 3. And that implies A1 is equal to 2. So in this case, you can express 1 over 3 as a linear combination where A1 is equal to 2 and all the other coefficients are equal to 2. Okay. And then the others are similar. You can find that. And so that is the space 3 expansion. Let me look at the other thing that I want to talk about. So here P is not divisible by 3. So we have AK is equal to 1, 0, 0. So here we actually, so there, Follin actually gives us a general conclusion is that if P is not divisible by 3, then AK is equal to 0 or 2. So in this case, since 1 is not divisible by 3, and we see AK, which is A1, is equal to 2. So that aligns with Follin's observation. Okay. So that is the base rate decimal expansion and how that links to the Cantor set. Okay, so also another observation is if X is smaller than Y, if only if, sorry, if and if there exists n such that a is smaller than bn and aj is equal to bj for all j that is smaller than n. Okay, and then now the Cantor set. Um, is a set of x in 0, 1 with 3 base. So x is equal, x is equal to summation aj 3 negative j with aj that's not equal to 1 for all j. So aj could be equal to 0 or 2 but not 1 because we removed the middle part. Okay. Right. So that. And then we have an proposition 1.22. I'm going to brief discuss with rather than writing rigorous proof. So there are 3 claims. The first claim is that C is compact. C is nowhere dense, and C is totally disconnected. And C has no isolated points. Okay, so that's and then for B, he's saying that the M of C is equal to 0. And for C is that the cardinality of C is equal to 0. So I'm going to use a different color. C is compact. This is true because C is closed and bounded. Okay. And then proof 2, C is nowhere dense. C is nowhere dense. What is for nowhere dense? If the closure is equal to the closure has empty interior, right? So C, the complement of C is another Cantor set, which does not have any open interval. I think so. When you're doing so, what do you do? You're doing this first, and then you're doing this. Then you're doing this, 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 and then your complement is going to be so first of all you have this. Then you have this and this. Oh, I'm sorry. I'm sorry, I said it wrong. So C is nowhere dense. That means the closure of C is C, since C is closed, and C does not have any non-empty C has empty interior, i.e. it does not contain any interval. Okay. And then C is totally disconnected. How to show this? The definition for totally disconnected, if you have x in one, if you have x does not equal to y and x belongs to A, y belongs to B, and A union B is equal to S. Okay, so take x in C and y does not equal to x, then there exists n such that like point is as we increase n, as we go down to the lower level, then eventually there is going to be an interval separate x and y. So there exists n such that 1/4 to the power of n is going to be smaller than x minus y, and therefore implies x is in C 1 and y is in C2, where C1 intersects C2 is equal to empty set. Okay. And then C has no isolated point. So what does it mean by saying that C does not contain any isolated point? Has no isolated. Well, the definition for isolated point is there exists X is an isolated point if and only if there exists a neighborhood of X such that the neighborhood does not contain any point in the Cantor set C. So we're going to prove Ci is a union of finite number of disjoint closed intervals of length 1/4 to the power of I. Right, so Ci is the union of a finite number of disjoint closed interval of length 1/4 to the power of I. So what do I mean? So for example, when I is equal to 1, what does the interval look like? So what is the length of each interval, right? So this is 1/3 is 1/3. And then what about I is equal to 2? So we have, so I know this is 1/3, this is 1/3, this is 1/3 divided by 1/9, 1/9, 1/9, 1/9. Okay. Okay. So it's not 1/4, but for example, this is 1/3, sorry, 1/3 to the power of 1, 1/3 to the power of 2, so it's 1/3 to the power of, and I probably should change this to 1/3. Okay, and let epsilon larger than 0. So we need to pick a random point. So let epsilon larger than 0, then choose n. Choose n such that 1 over 3 to the power of n is smaller than x minus y. Where is x? Oh, sorry, smaller equals than epsilon. Smaller equals than epsilon. Okay. And so let X be a random set in C. We want to show any random set in any point is to show there's no isolated point. We need to show for every point that there is there for all there exists for all neighborhoods there exists a point in Cantor Set that lives in the neighborhood of X. Okay, so then X is in some level of the Cantor set we call Cn, right? And so X is in In, where the length of In is equal to 1 over 3 to the power of n. Pick y that is not equal to x. We want to show there exists a point in the neighborhood. So we want to show the existence of a point in Cantor Set that is arbitrarily close to x, and then we choose y. So pick y that's not equal to x to be the end point of that interval. So y minus x smaller than 1 over 3 to the power of n, which is smaller than epsilon, and therefore there exists y in so epsilon is kind of like the neighborhood. Therefore, for all epsilon neighborhood of x, there exists y in the Cantor set such that y minus is in that neighborhood. So that means y and x are extremely close, and then we're done. Okay, so that's the part A. Let's prove part B. I think for this to prove, how do we express the Cantor set, right? We need to think about how do we express the interval. So for level 1, remember we have this, right? Sorry, we have this. Okay. So it's 2 times 1 over 3. And then that's level 1. Level 2, we have that is 4 times 1 over 9. And I think for level n, that is 2 to the power of n, 2 to the power of n, 2 to the power of n times 3 to the power of negative n. And then we need to sum up, right? Oh, or an easier way is to look the opposite. So level 1 is complement, which is 1 over 3, and then level 2 is let me see, this, right? No, level 2 is this. So I have 2 times 3 to the power of negative 2. And then 2 to the power of 1. Right. So therefore, C is equal to M1 is equal to M01 minus, let's do this, 1 minus, so level N here will be 2 is equal to 1 minus summation 0 to infinity. This is equal to 2 to the 0, 3, negative 1. Right, so 2 to the power of j over 3 j plus 1. Okay, and that is equal to what? That is equal to 1 minus 0 to infinity 2j 3j times 1 over 3, which is equal to 1 minus 1 over 3 times 0 infinity 2 over 3 to the power of j 1 over 1 minus 3 1 minus 1 over 2 over 3, which is equal to 0. Okay, so therefore we have done that the Lebesgue measure of Cantor set is equal to 0 and the cardinality. So notice, consider, recall that once we are showing something about cardinality, we need to construct the function. So recall that from, for example, p into x is injective and surjective and bijective. Is injective if and only if cardinality of Pn is smaller or equal than the cardinality of x. And then if it's surjective, that means the cardinality of Pn is larger or equal than this. And then we have cardinality. This is equal to the cardinality of x. Okay, so we have all these three things, and then we need to think about the function. So here, consider f from c to 0, 1. Okay, by fx is equal to this 1 to infinity bj 2 to the power of negative j. So this is base 2 expansion. So this function is surjective or bijective, I forgot. Okay, that is a bijection. Okay, here we define bi. Okay, so and then what do we do? Because it is injection, so the cardinality of C is equal to the cardinality of 0, 1. But the cardinality of 0, 1, which interval of subset of which R is equal to the cardinality of the real number, which is equal to C. Okay. Therefore, the cardinality of C is equal to C. Okay, and we're basically done with discussing the Cantor set, base 3 expansion of interval 0, 1 of the point 0, 1, base 2 expansion of the point 0, 1, and so just for the sake of completeness, the book also talks about Cantor function. So the Cantor function f is just the map that we defined earlier. It is a map extension of the map that we defined earlier from 1 by fx is equal to 1 to infinity bj 2 to the power of negative j. So recall that before we define C f to be this, right? And now we extend f to 0, 1. That means we extend the domain from C to the closed interval 0, 1 by defining constant on each interval missing from the Cantor set. So the key idea of the Cantor function is really like if you have a point, x in 0, 1, you should determine first is base 3 expression, and then remember that if any of the coefficient in that linear expansion is equal to 1, that means it is not a Cantor set. It's not belong to the Cantor set, and therefore you should replace the first one by 0. So basically, why we're doing that, we're trying to, that's basically the operation of the function f, the Cantor function f. We're trying to transform a set, a point in base 3 expression to base 2 expression. And now, of course, while doing that, we're moving it around. Okay. So we kind of like we were given a point in the Cantor set, and if it is in the Cantor set, then it is a constant. If it is not in the Cantor set, then we interpret that point as a binary digit, and then we write down the corresponding binary digit on 0, 1. So towards the end, you should have, for example, it is a set from 0, 1 to 0, 1, okay? And then, so I actually found a better representation of the Cantor function, like explicit function. So let's write this way. So fx is equal to summation 1 to infinity an 2 to the power of n. So this is a binary base 2 expression of decimal point on the interval 0, 1. And given that x is equal to 0, 1 to infinity of 2an divided by 3, and to that's base 3. And then in the Cantor set, where an, so here I can write this way. So an, where an belongs to 0, 2, right? Because this is the definition for a point to be in the Cantor set, the coefficient, the quotation mark coefficient can only be 0 and 1. If it's 0, if it's any of them is, if it is 1, then that means it doesn't belong to the Cantor set. So we're leading into the other case, x is in 0, 1 set minus c. And this is the supremum, y smaller than x, y is in c, f of y. So it is just a supremum. So if you are given, for example, on the integral, you are given an x, and x is not belong to the Cantor set, then you can like evaluate, you look at the point on the left of x, so which is here, right? And then on the left of x also, these are the Cantor set. So basically, you look at the supremums, and then, for example, the supremum among this point is the supremum over all of the Cantor set point in the Cantor set, and also the point left on the left of x is here. Then notice segment is constant. So basically, no. So basically, the fx is here. So if between this one and this one in the middle, it shouldn't have any. If it doesn't have any Cantor point, then it also takes the same value. So at the end, you will see on this interval, it is constant. And sorry, I just found a mistake when I was writing this. This should be an over 2. Right, this should be an over 2. Right. So let's think about 1 over 3. So 1 over 3, this point, 2 over 3, this point. So 1 over 3 is definitely in the Cantor set, and it can be expressed as 1 to infinity, and 2 over 3, this. Okay, and then so f1 over 3 is equal to 1 to infinity. So it's going to be 1 because all the an's are 2. So an divided by 2 is equal to 1 over 2 to the power of n. So this is equal to summation 1 over infinity. 1 over 2 to the power of n, which is equal to 1 over 2 times 0 infinity 1 over 2 to the power of n. And this is equal to 1. So it's equal to 1 over 2 times y is equal to 1 over 2. Therefore, we know that 1 over 2, this point has this. And notice that we already know this. So this interval does not belong to Cantor set C. So for example, if you pick up a point over here and then follow the definitions over here, right? You have follow the definitions over here. So x is in 0, 1 set minus c, then is equal to supremum y is smaller or equal than 1 over 3, and y is in c. I'm sorry. So for example, here is equal to 1 over 2. So y is smaller or equal than 1 over 2. Y is in the Cantor set of fy. So you look at all of this, right? So it is equal to supremum of the set of y. Y is smaller than 1 over 2, and y is in the Cantor set C. And this is equal to supremum of fy. Y is smaller than 2. So you look at all the Cantor set and you pick the maximum, right? And then we know ahead of time, and actually you should prove it. The Cantor set function is actually non-decreasing. So we know this. We know that this point is a supremum because this is a because it looks like this, right? And then we were doing, of course, you should pick up this point, and which is 1 over 2. Just gonna say this is equal to f 1 over 3, which is equal to 1 over 2, and therefore it's 1 over 2. And notice our argument applies for every point on over this interval. Okay, so we have this. And then therefore you can see on the graph of the Cantor set. So similarly over here, right? We should find something looks like this. Right. Right, those are not belong to the Cantor function, and you should look at what is the value evaluate at this Cantor point. What is the value evaluate at this Cantor point? So overall, it's not accurate, but it's going to be something like this. And then yeah, it should be something like this. Okay, I hope that helps a little bit. Thank you for watching, and let me know if I made any mistakes.